So let's continue our exploration of TCP. Here's something I should repeat here, is that when we see the acknowledgement field has jumped from 0 to 2, here the 2 means everything up to number 2 is acknowledged. The acknowledgement field is a single field, so of course it's cumulative. It means I'm acknowledging everything up to number 2. So here the destination has saved acknowledgement by not sending one packet here of acknowledgement here. It has here one single acknowledgement that's acknowledging everything, more precisely the 2 previous packets here. Here are how things fit together when we do trace with Wireshark and something else. We will see everything we've discussed before, plus the fact that now typically communication occurs in both directions. So here A is sending data to B. So we see that here 500 bytes are sent, but B is also responding with some data. Not just an acknowledgement, but some data, which is a typical case. You go to a web server, you send a GET and a number of information in the request, and the web server responds with some data here. So there is, therefore, an ACK field and a window in both directions. But here this ACK 101 means A is ACKing data that has been sent by B previously. So the ACK and the window are for the reverse direction. Here we see also what is called a pure ACK. When this packet is received, it is ACKed, and we see there is 0 byte of information, means it's a pure acknowledgement. TCP does that if it has nothing to send. Here it has something to send, but here and here it had nothing to send. Every packet that is sent that corresponds to some data will be repaired if the packet is lost, because that's the job of TCP. Now, a pure ACK might not be repaired. If you send this ACK here, if B is not sending, does not have any data that has been sent and is not acknowledged, it has no reason to send anything. So if A is not sending and B is not sending, nothing will happen. So TCP is a lazy protocol. If there's no reason to send any packet, you don't send anything. We have seen that this may cause problems when the window is 0, for example, and we need specific mechanisms to handle such cases. A small question here that will be useful later when we study congestion control. By controlling the window size, we can in some sense also control the speed at which a sender is sending data. So the question is about this one. If we want to fully use the available capacity, so assume between S and R there is a certain available capacity C, and we want to make sure we fully use it. So we avoid the problems of the stop-and-go protocol here. Is there a solution in the proposed answers here? If you say B, you have a problem that you should fix now. Think about the units. It's like in physics, right? A window is what? Is bits or bytes or packets. It's units of data. RTT is a time, and C is time divided by, data divided by time. So the answer A, from the viewpoint of the units, matches. Answer B and C don't. So if you answered B or C, you should not have done that, right? You know those answers are incorrect. Right? So the only choice is between A or D, which is of course very nasty. If I give a quiz with none of the above, of course it's very nasty. Don't worry, you won't do that in the quizzes on Friday. The answer is A here. Here I have a very shallow and fast proof, but it gives the idea. It's again the problem of the stop-and-go protocol. The issue is what is the amount of data that is in flight. If the window is larger than the round-trip time here, the bandwidth delay product, sorry, which is the amount of data that can be in the pipes here, then we will have a pipeline here. when the acknowledgement of the first packet comes, I'm able to send the second, and I can send at a rate where I'm never waiting. I'm never waiting for an acknowledgement like I'm doing in the stop-and-go protocol. So in that case, if the window is larger than the bandwidth delay product, the rate at which we send is the rate of the line, is the rate C. If the window is smaller, this is what happens. I send at the rate of the line, these two red arrows, then I have to wait for the acknowledgement of the first one. If I had not waited, I could have sent the second packet, but I have to wait here. So if the window is smaller, then the rate at which we can send is in fact, if we do similar analysis as we did for the stop-and-go protocol, the rate at which we send is the window size divided by the RTT. This is an important intuition. This is how congestion control in the internet works. In congestion control, what we will do is we will artificially manipulate the window size in order to achieve a given sending rate. So of course, if the channel capacity is C, if you're connected to the internet through an ADSL line at 30 megabit per second, you will not send more than 30. But if we want to control your rate, have you send a bit less, then one way to do it is to manipulate the window here. By reducing the window, then we will reduce your rate. But of course, the round trip time comes into the equation. So we will come back to this a bit later. Right now, let's have a look at how TCP is used from a programmer's viewpoint. It's very similar to UDP with a few added complexities. The first complexity is that in TCP, there is the concept of a connection. Connection is a very vague term. It can mean different things. But the idea of TCP was to do the equivalent of a telephone circuit that existed in the 70s when those things were invented. The most frequent way to connect two computers at that time was not through the internet. Do you know what it was? You never look at those movies of the 70s where people interconnect computers, or the 80s, let's say. You would use a modem. So you would call, you have a computer in A, another computer in B. A calls B by telephone, and then you put, you connect the computers through the telephone line. The very first modem was simply acoustic. So you had a physical layer that is sending sounds that are put into the telephone lines. The sounds arrive at the other end. You decode the sounds, and this is how you get up to several kilobits per second. So you establish a connection. And the model of TCP is that one. With TCP, we have A that speaks to B, and they establish a connection. It's like calling over the telephone. So when you call over the telephone, you call first. So what do you do when you call? You send a message to someone saying, I want to speak to you. And if the other one agrees to speak to you, so now you use WhatsApp or whatever, if the other one agrees to speak, you can start to speak, but you don't start to speak immediately. That's exactly what happens with TCP. First, with whoever wants to talk, sends a connection opening request, and this has to be accepted. And if this is accepted, only then we can talk. It's a bit more complicated because with TCP, we don't know whether a message that you have sent can be lost or not. So not only you need to send a connection request and wait for the acceptance, but also you need to hack the connection acceptance because this packet might be lost here. So so that's the first reason is because of the mental model, but there is a physical reason for that, is that in TCP, we need to initialize a number of things. You cannot simply start a TCP using data over TCP. We need to initialize things. What are the things we need to initialize? Well, the major one is the window. When I saw all the figures before, it was important to know whether you can send a packet or not, and to know whether you can send a packet or not, you needed to know the whole history. So you cannot come in the middle of those cartoons if you don't know the history. You need to know what packets were sent and which one were acknowledged before. So you need to know what is the initial value of the window when you start a connection here. So this is essentially the purpose of this, is to force all window mechanisms to be reset here. So this is done by doing what is called a three-way handshake. We need to send 3 different TCP packets. They're all empty, those 3 packets in principle, although we will see that in practice, in some cases, you can put some data in it, but the standard way of using TCP is that you send what is called a SYN packet. It's called a SYN packet because it contains one bit in the TCP header that is called the synchronization bit. Connection in the setting of where we are is often taken as a synonym for synchronization. Two things are connected if they have synchronized data. I mean, if they have data that is the same. How do you get data that's the same in two different systems? It's very hard. You need to send the data, an acknowledgement, make sure you agree. So you need an agreement protocol, which is what we do with TCP acknowledgement by, here I'm saying, I would like to start sending data, and I signal what is my initial sequence number. To avoid easy replay attacks, the sequence number is typically a random number. And in the reverse direction, the same thing happens. I accept and I give you my initial sequence number. And I also acknowledge yours here so that you know that your packet has been properly received. And you need to acknowledge mine. And we see there is a small exception here. The acknowledgement field here is the previous +1, even though there is no data in the SYN. This is because in principle, when we send a packet that has 0 data, we don't expect this packet to be acknowledged. We don't wait for anything to be acknowledged. So here we do, but here for the SYN packet is different. We want the SYN packet to be acknowledged. So the standard says it is as if there was 1 byte in the SYN packet, even though in practice there is probably 0 byte in it. It's only when this has completed that you can start sending data. So there is an overhead of using TCP. If you have 1 byte to send or 1 request, like you do with DNS, when you ask a question to a DNS server, you don't use TCP because for using TCP, you would need to have 3 packets successfully sent before being able to send any data. And since you create a connection, that means you create some state information that is synchronized on both sides. The receive buffer, for example, all those pointers that are explaining what are the sequence numbers that have been received, ACT, all that stuff, they use up resources on both systems. So if you use resources, you have to make sure you can release them if they are not used. So the traditional way to do that is to close a connection, and TCP does it. Now, because there are in fact 2 connections in TCP, 1 for every direction, you can close individually each of the 2 directions. It may be that A has still some data to send, B is finished sending, so B says, stop, now I close the connection, but A still has some data that is not sent, so you will have to close them in both directions, and there are lots of possible cases that can occur. It's not necessarily exactly in this order, but that's the standard way. There's another way to close a TCP connection is to send a reset that occurs when A talks to B and over a TCP connection, and all of a sudden the socket is deleted in B, for example. Then the operating system receives a TCP packet for a port number, and there is no socket associated with this port number. Then, in that case, the operating system will send a reset saying this is not working. Well, that's not the nice way to close, but that's sometimes the frequent way. Here is the TCP header. So TCP costs at least 20 bytes. IP costs 40 bytes if we use IPv6, TCP 20. So to send 1 byte of information, you need 60 bytes of overhead with TCP and IP here. The main things that are in the TCP header are the sequence number, 32 bits. 1 line here is, as usual in all our packet formats of internet stuff, is 32 bits. The sequence number and the acknowledgement number. And of course, we also have the port numbers that are 16 bits each. And there's a number of things that we will not discuss, and the window size, which is here also. And of course, not of course, and the SACs that we've said are extra to the 20 bytes. So very often the header will have more than 20 bytes. The options contain SAC, other things like the negotiation of the maximum packet size that is done at the beginning in the SYN packet. One of the things that is sent is in the options is what is the maximum packet size that I would like to support. Because perhaps I am running IPv6 Therefore, my maximum packet size is IPv6 tunneled in IPv4, or for whatever reason, I may support maximum packet size that are smaller than the standard. So this is sent by this one. This one takes the minimum of what it can support and what this guy offers, and in the SYN ACK, we will have the MSS, the maximum packet size that is accepted for this connection. When we use TCP sockets, we don't see the packet format, but we're exposed to some of the details because we need to open a connection. And this is visible through the connect call that we did not have with UDP. So it starts similar to UDP. So we create a socket. Now, when we create a socket, we have to specify whether it's IPv4 or IPv6, but also whether it's TCP or UDP. In fact, there are also other sockets, but they're not frequently used. You do the bind, which is the same thing as before. And then if you are opening the connection, you do what is called a connect. The connect sends no data, but it tries to open a connection with the other end. So the argument of the connect is the destination address and port numbers. And when you send the connect, when you do a connect, you don't send any data, but your operating system will send data for you. It will send a SYN, expects a SYN ACK, and send a SYN an ACK. And as long as this three-way handshake has not completed, the connect does not return. So when you do a connect, you block on this connect until all that thing happens. Only then you can do a send. On the server side, it's even worse. You need to do two things. You need to do a listen. Listen means create what is called a queue, the listen queue, which is the queue of all the connection opening requests, all the SYN packets. For some reason, you need to do it. I mean, I believe in Python, we might not be exposed to that. And once you have done that, that means you have created a socket on which you are accepting to receive connection requests, on which you're accepting to receive SYN packet. That's what a TCP web server typically does. This is what a server is. So the definition of a server is a system that is waiting for things to come to that system. So a TCP server is a system that does a listen, essentially. Now, listen means you are ready to receive SYN packets. Whenever one SYN packet comes, you can consume it with an accept. So if you don't do an accept, the SYN packets are simply queued in the listen queue, in the socket buffer, and nothing happens to them. Now, if you do nothing, those connections will abort sooner or later. So you accept that you assume that this system will do an accept, and the accept means I consume one SYN request from the queue, if there is one. If there is not, I block until there is one that comes. If you're a server that nobody contacts, then the server program hangs and waits until a request comes. When a request comes, you consume it, and something else happens that we're showing here. On the client side, it's very easy. Once you return from the connect, you can do a send, like on a UDP connected socket. Now, we don't need to give whom we're sending to, because all of this has been done in the connect call here. So observe, in UDP, there is also a connect call, but in UDP, the connect call does nothing. It does only local caching of information. In TCP, the connect call truly does stuff that may fail, for example. A UDP connect may succeed even though the other system does not exist, for example. You have no guarantee that it will work. Whereas a TCP connect will work only if the other end accepts your connection. That's the first difference. The second difference is here illustrated by this pink color here. So the pink color means that when you do an accept, the operating system creates a new socket. So a new socket is created with a new socket buffer, which is on the same port number, the same everything. So if you write a TCP server program, you have to expect that you will have multiple sockets to handle. One of them is the socket you use to accept incoming connections, and the other ones are the sockets you use to do the work, to do the communication here. So there is what is called forking of a socket. A new socket is created that inherits all the attributes of the previous socket, and it is on this new socket, now it's S2, so what the accept call, you see, has a return code which is a pointer to a socket, or depending on the programming language you use, it may somewhere in the return of the accept call, you have the information of the new socket that is created by the accept call. It is the accept call that creates the new socket. So now your program has to continue doing the job on this new socket here, and then if it's a web server, it will send data, perhaps a bit more, receive and send from the client, and when this is done, we'll close here. So that's a very simple server. Probably there is no server that runs like this, apart from those we can do in labs exercises, because this server can handle only one client at a time. Right? So hopefully the web servers are able to handle more than one client at a time. So this is the very typical way this would be done. When you are writing the code of a server, typically after the accept, you create a new thread. Typically, you could create something else, but some form of parallelism such that a thread of execution will be able to work with this socket. And then once this thread is created, you can quickly come back and accept another one and create a new thread here. So you will have typically multiple threads, multiple sockets, that are all connected to the same port number, the same local port number, and the same IP address. But each of the sockets that are handled in each of those different threads are connected to different remote systems. So they are different sockets. And there is one buffer for each of those, which makes sense. Because if you think of TCP, the way TCP works, we need this reassembly buffer per TCP connection, not per server. So this is why we must have at least one buffer. And the way it's done is by having one socket here. Here's the mental model of how sockets are in a standard machine. Again, like with UDP, first, TCP sockets are different from UDP socket. If you have a TCP socket that's listening on port 53, it's not the same as another one that's listening on UDP port 53. You can have a program that listens on TCP port 53, another program that listens on UDP port 53. The two are different. They are different worlds. The same is for IPv4 and IPv6. And here I'm showing in the IPv4 world the listen queue, which is the non-connected TCP socket, is non-connected because this is the queue we use before we have established a connection. So that's the first socket that is done by your program starts. All the SYN packets will be sent to this socket, and this is where all the hard work of opening the connection is done. And whenever a connection is open, new sockets are created, one per connection. So those pink things is where the blue sockets. And each of those pink sockets is associated with both local and remote IP addresses and port numbers. So a socket, one of the pink sockets, is associated by those four elements, 2 IP addresses and 2 port numbers here. TCP packets, as we know, are called segments. The segment must have a maximum size, which is system dependent. As we will see a bit later, it may also be dependent on the path between 2 machines. We will see that there exist sophisticated mechanisms to make sure that the segment is not too large, not just because of the local machines, but also because of what happens in the path. What can happen in a path? Normally everything is on Ethernet, so 1500 bytes. But sometimes you do things like authentication, encryption. So if you encrypt all your data in an IPsec tunnel, for example, we'll say a few words about that towards the end of the course, then the usable part for TCP is smaller because you have all the encryption mechanisms. Also, sometimes when you use virtual private networks, we may put the IP packets in IP packets, for example. This is what happens when you connect to the EPFL VPN from your house. Your IP packets will be sent inside UDP an encryption mechanism inside UDP sent to a VPN server at EPFL. And of course, this reduces the size, the available size of the IP packet. Also, there are exotic technologies in the industrial world that use much smaller packet sizes. So in IPv4, you can have very small packet sizes. The minimum size can be as small as this number, 536. In IPv6, the minimum size is 1280. So 1280, the normal size is 1500 for IP packets. But if you have all those encapsulation, encryption, authentication, etc., the bound we believe today that is safe is this one. So any system that runs IPv6 should be able to accept packets of this size, perhaps larger one if you want to optimize. For example, at CERN, when they do this large number experiments where they create zillions of collisions and they have zillions of bits, zeros and ones, and they try to detect whether there's a new quark that exists. So they have zillions of packets to shuffle around. So in order to make that possible, they create what is called jumbo packets. So they have special equipment that is able to have packets that are not 1,500 bytes, but perhaps 100,000 bytes. That saves CPU processing. Doesn't save the bandwidth on the lines, but it saves CPU processing. So this is, as I said, negotiated at the beginning of a connection. The two ends have to agree what is the packet size or the segment size. And then it's the job of TCP to break the data into containers that are not exceeding the MSS. And as I stress here, it's TCP who segments the data. It's not visible to the application. You can try to guess it by a number of mechanisms, but in principle, it's not visible to the application. If the MSS is 1,000 and you create a message of 1,001 byte, TCP will create two segments. If you create 999 or 1,000, it will create only one, but it will not be visible to you. As I said several times, so the TCP offers a streaming service. Concretely, it means on the sending side, whenever an application writes, TCP accumulates the bytes into the sending buffer. You could think, well, the normal thing is if the application writes 1 byte, then TCP should send 1 packet. But this might not always be efficient because if an application is writing byte by byte, for example, then TCP might as well, if the application is doing that very fast, the TCP might as well gather a number of bytes to create only 1 packet. Instead of sending 500 packets within 500 milliseconds, it might be better to send a smaller number of packets that have more bytes. In other words, TCP has the freedom to create the segments at the source. Now there are trade-offs, and there is an algorithm called Nagel algorithm that we will not discuss in detail. So one of the heuristics in TCP is when to send a packet. So the job of TCP, as you see, is not very simple. TCP is probably the most complicated protocol in all the ones we will see. So one of the things to decide is when to send a packet. So the application is writing things in the buffer. I can be very aggressive, and as soon as I have 3 CPU cycles, I send something. But by doing that, I might be creating a lot of very small packets. So the heuristic is typically to avoid sending small packets, too many small packets one at a time, by having small timers that will wait a bit before accepting to send small packets. Right. That's on the sender side. On the receiving side, the same thing happens. Data accumulates in the receive buffer. We have seen that one of the reasons for keeping them is that they're not in sequence. Another reason is, of course, the application being perhaps too slow to read it. But the main thing that I'm stressing here is that the data is not marked. So you just have again, the semantic of sockets is exactly the same as file. A socket is like a file, except it's a file that is created on the fly. When you read from a socket, it's like reading bytes from a file. It's a dynamic file it's like reading bytes from a file that somebody is constantly writing into. So in particular, you don't know if several small pieces of data was sent by A, whether B will receive them in the same way. So those of you who are familiar with C, pure C programming, you know that if you have a string of characters, you should put a null byte at the end. Right? So if you have a long string, you send it, and TCP breaks it into two. One way to crash a program is to read. You call from TCP, you read everything that has arrived, and you print it. If you do that, if you're unlucky, the null character is not in the block because the sender has perhaps sent one block, but TCP has decided to segment because of all the arguments we said before. So when you receive it, you don't know whether you're receiving the full block. So when you read strings of characters using TCP, it's very clumsy. You need to read byte by byte until you see a 0. Right? It's very ugly, right? But this is how you read bytes in C with TCP. In more modern things, you have MIME headers that will give you when things start and when they close. But this is so the TCP service is streaming. In particular, there is head-of-the-line blocking. If one packet sent by A is lost, like we have seen in the many cartoons I've shown before, all the packets after that have been received are not available to the application. This is called head-of-the-line blocking of TCP on the receiver side. Right? It might be a problem from some applications. Which applications that I'm listing here do you think it might be a problem for? And the majority says F, which is, I believe, the correct answer. So if you have one version of HTTP that sends, so you download one HTML page. The HTML page is typically several objects that are embedded and may have images and that are different files. One old way to do it is to have one TCP connection per object, which is very slow. Another way is to have a single TCP connection, which is faster because you have only once the overhead of displaying. However, with B, then head-of-the-line blocking will be a problem. If you are displaying the page and there is a script somewhere and there's one bit that is missing, then you will not display it, and the rest of the page, or the images, everything will not display here. Whereas if you use A, you will have all the different parts that are displayed in parallel. So that's one of the serious drawbacks of TCP today, and that motivates variants that we will see a bit later called QUIC. Another example is this one, a real-time streaming application that is typical of industrial environment. You have sensors that sense some quantity, and if it's temperature, you send one reading every few minutes, you don't care. But if you're in a chemical process or a smart grid, you can do readings several times per second. So you have a stream of measurements that come. Typically, you use UDP. If you use TCP for that, the problem is that if one measurement is lost, TCP will try very hard to repair it, and while repairing, will not deliver the next one. But if you're controlling a process, you don't care about the lost one if there is a newer one. If there's a new measurement that comes, what you want is to have the new measurement as soon as possible. The old one that is lost, you don't care anymore. You have better and newer information to decide what to do. It's what you do in your car. When you drive by wire in your car with autonomous cars, they have to decide whether to press the pedal for braking or accelerating or turn or whatever. They have to have very fast response about what they see. So for such things, TCP is not good. Yes? For B, because assume you go to a web page and that has several embedded elements, and you use only one TCP connection. And this TCP connection is about, I don't know, a logo in the banner. And there is one logo in the banner that is a separate file, very typical case, right? And assume one packet of that is lost. Then the rest of the page will not display. So you click on the web page and you see nothing because it's trying to repair a logo that you frankly don't care. You might as well see the page with a placeholder for the logo, and perhaps by the time the logo comes, you've turned to another page anyhow. But if you use TCP with one single connection, you will have head-of-the-line blocking. There's a lot of advantages of using a single TCP connection. I mean, the server has much less work to do. So as a server designer, you prefer to use one single TCP connection for sending all the information that's on a web page. But as a user, the latency experience is much less good because of the head-of-the-line blocking. So that's the price to pay for having TCP. I mentioned server several times. What is a TCP server? And everybody almost says A, which is correct. Right? So the word server really comes from the interaction of distributed systems, where the only way we know how to make two machines communicate is to have one be in standby mode waiting for something to come. That is, one is called the server, and the other one is called the client. That's the only way we know how to make things work. Now, concretely, very often people call a server the machine whose main role that is visible from the outside is doing that. So a web server is a TCP server as well, but as we will see a bit later, there are perhaps more complicated interactions. You all know of peer-to-peer applications that are both clients and servers, for example. Why do we have both UDP and TCP? Well, we said some examples like voice applications and PMU streamings would prefer to use UDP. Why? Because if you miss one frame, it's not necessarily that bad, correct? Because TCP will repair it for you, but there is a price to pay for TCP. We've seen head-of-the-line blocking. Another one is the delay. So if you do YouTube streaming, you don't care about the delay. In fact, when you watch a football match over TV over the internet, you have a delay. You see when the goal is placed, you see it a few seconds after people who watch it on TV live. This delay is in order to mask all the variability of TCP. TCP introduces a variable delay. Whenever something is lost, all of a sudden, it will take a lot more time to deliver the data. So the rate at which TCP delivers data is not fixed and constant. So if you have a source that is coding video at a constant rate, video is never at a constant rate, but as a first approximation, assume it at a constant rate. At the TCP side, it will be constant until there are losses. And when there are losses, then it will be delayed, and then it will be faster because all of a sudden a big block of data is made available. So YouTube, for example, when it uses TCP, which is not the most current case, but when it uses TCP, will use what is called a playback buffer. Before you watch the TV, the first thing you do is you store some amount of data for several seconds of video. And then you wait for that. So if your several second is large enough, this will amortize the variability in delay. Right? If it's not large enough, then it will hang, and you will need to refill the buffer here. This is what you do if you do TCP. Now, if you do interactive video or audio, that is not okay. If you want to have very little latency, we consider that interactive audio communication is hindered if the round-trip time is above 200 milliseconds. If it's larger than that, it starts being I speak, I wait, I see your answer, I wait. So when you see on TV two people speaking, and one journalist is in Lebanon, the other is here, you see that thing. One speaks, you see the other one is doing nothing. She's listening, but she hears that 1 or 2 seconds after you. Right? So that is typically what you do because they use the internet and they have a TCP or protocols like that. If you want to do very high quality interactive things, you have to have low delay. So what is typically done by Skype and others is to have very smart coding and UDP. And the way they handle losses is by playing with the coding. Typically, you code the video and the audio at several resolutions. And when I send you one packet of high resolution, I also send a repetition of the previous packet at low resolution. So if a packet is lost, I still have one packet, the packet before or the packet after, that has some low resolution that can mask the thing. And lots of tricks like that you will see in the signal processing courses. Other examples that don't use TCP, that we mentioned many times, is the ones that have very short interactions. If you're sending one message and expect a response, don't use TCP. You might as well use UDP, and if the response doesn't come, you will need to do something anyhow. So this was our first iteration step on TCP. Now we'll do 2 more rounds, one now and another one after we've done the theory of congestion control. So what we will discuss now and next week is what I call the more TCP bells and whistles. So TCP is a protocol where there's a lot of freedom of implementation. So large companies like Microsoft, Google, Apple, they all have their own version of TCP that has to be interoperable with all other versions of TCP. And one of the things where they differ is, for example, when to send a packet. We will not see that in detail. When to send an ACK also. If you receive lots of data, we have seen that the ACK is cumulative, so I can wait until I've received 5 packets to send 1 ACK that will ACK everything, or I can be very responsive and send 5 ACKs. If I'm very responsive, I'm creating a lot of traffic and a lot of work. If I'm not very responsive, I'm creating latency, because there is a trade-off to do somewhere. There are specified algorithms to do that. The one we will see next week, so that's a teaser for next week, is how to detect a packet loss. So this seemingly simple thing, in fact, is not as simple.